A star 1,470 light-years away is flickering so strangely that serious astronomers had to ask, could this be aliens? Not as a joke, as a line in a peer-reviewed paper draft. Tabby Star, officially KIC 800-285-2, can dim by more than 20% for days or weeks at a time, with no clear pattern and with no matching brightening. No other normal star we know behaves like this. If a civilization ever built a Dyson swarm or some other megastructure around its sun, this is exactly the kind of bizarre light curve we might see. So what is this star actually doing? Tabby Star sits in the constellation Cygnus, a fairly ordinary F-type main sequence star a bit hotter and bigger than our sun. It became famous because of Kepler, the space telescope that stared at over 150,000 stars, measuring their brightness every 30 minutes for 4 years. Kepler's job was to find exoplanets by watching for tiny regular dips in starlight as planets crossed in front of their stars. Earth crossing the sun would block less than 1% of its light. That's the scale Kepler was tuned to detect. When astronomer Tabitha Boyajian and colleagues combed through Kepler's data, one star looked utterly wrong. Instead of neat, periodic dips like clockwork, Tabby Star showed wild, irregular plunges in brightness, 5%, 15%, even around 22%, lasting from hours to many days, with no repeating period. A Jupiter-sized planet only blocks about 1% of a sun-like star. To dim a star by 20%, you need something enormous, or a lot of somethings, crossing the line of sight. And yet, there was no infrared glow that you'd expect from huge amounts of warm dust. To understand why this was so unsettling, it helps to recall how transits normally work. When a planet passes in front of its star, the dip in brightness is tiny, symmetric, and repeats with the planet's orbital period. From that pattern, you can infer the planet's size, orbit, and sometimes even its atmosphere. Kepler found thousands of exoplanets this way. Their light curves look like clean, shallow bites taken out of the star's brightness. Tabby Star's light curve, by contrast, looks like a city skyline after an earthquake, jagged, uneven, and never the same twice. On top of the short-term chaos, long-term monitoring suggested the star might be slowly fading over decades. Archival photographic plates from the early 1900s hinted at a gradual dimming, and modern surveys like ASAS-SN and Gaia have tried to track this. The evidence for a century-long fade is debated, but there is consensus that on timescales of years, the star's average brightness changes by a few percent. Stars like this are not supposed to do that. Main sequence stars are usually incredibly stable, with luminosities that barely budge over human lifetimes. So what could cause such strange behavior? The most conservative idea is dust. If clouds of fine dust grains orbit the star in clumps, they could block large chunks of light when they pass in front. Crucially, small dust grains block blue light more than red, a phenomenon called wavelength-dependent extinction. Observations during some dips show exactly this. The star gets redder as it gets dimmer, which is a strong clue that at least part of the effect is caused by dust, not solid opaque objects. But this dust can't be just anywhere. If it were close to the star and abundant enough to block 20% of the light, it should absorb that energy and re-radiate it as infrared glow. Telescopes like Spitzer and WISE looked for that excess infrared emission and found almost nothing. That means the dust must either be very cold and far from the star or present only in short-lived, sparse clumps. One hypothesis: swarms of comets or fragments from a disrupted icy body, shedding dust as they fall inward on eccentric orbits. A giant family of comets could, in principle, create irregular, deep dips. But to block that much light, you'd need an absurd number of them, far more than we think typical planetary systems host in one tight region. And you still have to explain the possible long-term fading. Other ideas involve debris from a recent planetary collision, or a warped precessing disk of material around the star. Each model can match some features of the light curve, but not all. The system might be a messy combination: dust, debris, maybe even intrinsic stellar variability we don't fully understand yet. Then there's the hypothesis that made headlines: an alien megastructure. If a civilization wanted to capture a significant fraction of its star's energy, it might build a Dyson swarm, countless collectors orbiting in complex patterns. As they move, they would block starlight in irregular, non-periodic ways, potentially producing deep, asymmetric dips, without much infrared glow if the structures are efficient radiators. This idea was speculative, but testable. Radio telescopes, including the Allen Telescope Array, pointed at Tabby Star, searching for narrowband radio signals or other technosignatures. So far, every search has come up empty. No obvious artificial signals, no repeating beacons, no smoking gun. That doesn't rule out technology, but it makes the megastructure explanation less compelling than natural dust and debris. Also, the color-dependent dimming fits dust better than solid opaque panels. If you were designing efficient collectors, you wouldn't build them to selectively block blue light more than red. Still, Tabby Star became a case study in how to seriously evaluate an aliens hypothesis. You propose it, derive observable consequences, and then go look. Beyond the drama, this star matters because it forced astronomers to admit that our catalogue of stellar behavior is incomplete. Kepler and later missions like TESS revealed a zoo of variable stars. But Tabby Star sits in a weird corner of parameter space, a seemingly normal F-star with a uniquely chaotic light curve that pushes theory. How do dust dynamics, radiation pressure, and orbital mechanics interact to create such patterns? How common are these systems? And have we simply missed others because we weren't looking closely enough? It also sharpened the field of technosignature research. Instead of just listening for radio beacons, we now systematically scan light curves for anomalies, non-periodic dips, unnatural regularities, or energy budgets that don't add up. Projects like the Breakthrough Listen initiative and citizen science efforts such as Planet Hunters have used Tabby Star as a template for weirdness searches. Even if this particular star turns out to be 100% natural, the methods developed around it may be how we eventually spot something genuinely artificial. Today, the leading view is that Tabby Star is obscured by complex evolving dust structures, possibly from exocomets, collisions, or a disintegrating body, combined with subtle stellar effects. But the model is not fully nailed down. The exact geometry, the source of the dust, and the reason for any long-term brightness changes are still under active study. New instruments, especially those that can monitor the star across many wavelengths simultaneously, are slowly tightening the constraints, ruling out some scenarios and refining others. The deeper question lingers: how would we truly know if a light curve was shaped by intelligence rather than geology, chemistry, or gravity? Tabby Star taught us that nature is often stranger than our first guesses, and that alien megastructure should be the last explanation we reach for, not the first. But it also gave us permission to ask that question carefully, with equations instead of wishful thinking. Somewhere out there, another star might be flickering for a reason we can't yet imagine. And when we're ready to understand it, we'll talk about it here on Terra Nova.